In this video, we're going to go over how to evaluate the following indefinite integrals. Starting with part A, we have the indefinite integral of 4 over the square root of 1 minus 4x squared dx. Now what most people might be tempted to do is to use u substitution here. However, this function is already simple enough, so we don't really need to do that. However, I see that we have a constant 4 here, and using the constant multiple rule, we can simply take this 4 and move it out in front of the integral sign. And so by doing that, we're going to get 4 multiplied by the integral of 1 over the square root of 1 minus 4x squared. Now, something that a lot of people might be tempted to do is to rewrite this in a different way such that you can take power rule. Some people might rewrite this as 1 minus 4x squared to the power of negative a half. However, you cannot do that in this case because this is one of those antiderivative rules that you just need to memorize. And so the antiderivative of this follows the format of arc sine x plus c. And so that's what we're going to do here. However, first I need to figure out how else I can rewrite this such that I have brackets raised to the power of 2. Well, I know in order for me to have gotten the x squared, there had to have been an x here. But what about the 4? Well, there must have been a 2 here, and this is equivalent to 4x squared. So we're going to rewrite it like that. So we're going to say 4 multiplied by the integral of the 1 over the square root of 1 minus 2x all squared. And now this follows that format. So we're going to say 4 multiplied by arc sine 2x plus c. However, we are missing something. We just have to divide this by the derivative of the inside. And so the derivative of the inside is just 2. And why do we have to do that? Well, you have to do that because if you were to take the derivative of this as it is, we would get 1 over the square root of 1 minus 2x squared. And then multiplying by the derivative of the inside, we're going to get a 2. And so the original function does not have a 2 in here. So in order to compensate for that, we need to divide by 2. Or in other words, we're going to multiply by a half in order to get rid of that 2 that we just added. And so we can further simplify this to 2 arc sine 2x plus c. And this is your most general solution. And if you don't believe me, try taking the derivative of this, and I can guarantee you, you're going to get this again. Now moving on to part B, this one is a bit more complicated because we have an x term in the numerator. So even if I pulled this 4 out in front, I would still have this x in the numerator, which is going to cause some issues, obviously. So for now, let's just pull out the constant out in front. And we can say this is 4 multiplied by the integral of x over the square root of 1 minus 4x squared dx. And so for u substitution, the goal here should be to get rid of the x in the numerator, because this is the thing that is causing us some issues right now. And so the easiest way to do this is to just set u equal to whatever is inside the square root. So we can say u is equal to 1 minus 4x squared. And so taking its derivative, we get du by dx is equal to negative 8x. Now I want to get this in terms of dx, so in order to solve for dx, I'm just going to multiply both sides by dx, and I get du equals 8x, negative 8x dx, and then solving for dx, we get du divided by negative 8x is equal to dx. Now, as you get better and better at these questions, you can just skip from this step right to this step, and then you can go from that step to this step. As you get better and better at this step really isn't necessary. You can just save some time and go straight to this. And so now we're going to use the substitution and replace the x. So this stays, and then we're going to have root u. And then replacing dx with what we just solved, we're going to have du divided by negative 8x. And as you can notice already, the x's just simply cancel out. And then inside the integral, we have a constant of negative 8. And so what you can do is you can take this and you can pull it out in front of the integral sign and multiply it with the 4. And so when you do that, you're just going to get negative a half multiplied by the integral of 1 over root u du. However, I want to rewrite this in such a way where I can take its antiderivative more easily using power rule. And so I can rewrite this as like u to the negative a half. And then using power rule for integration, we know that we just add 1 to the power and divide by that power. So we have u to the 1/2 divided by 1/2, which is the same thing as multiplying by 2. And as you can see, the 2's just simply cancel out, and we're left with negative u to the power of 1/2. And don't forget your constant integration c. I always forget to add that. And then we can just replace u with 1 minus 4x squared. And I'm going to change this to the square root that we're usually used to. And so this is your most general solution. And if you don't believe me, try taking the derivative of this, and you're going to get what you started with. Moving on to this example, originally I was planning on making this not a perfect square because this is really similar to part A. So why don't we change this to something like 11? And just because we're replacing it with 11 does not mean the question is necessarily harder. It's just that 11 is not a perfect square anymore. So following the previous steps, I'm going to pull this 11 out in front using the constant multiple rule. And so we get 11 multiplied by the integral of 1 over the square root of 1 minus 11x squared dx. And once again, I want to come up with a way to rewrite 11x squared such that I have something in brackets to the power of 2. So obviously I know in order to have gotten x squared, there needs to be an x here. And to have gotten the 11, I could put a root 11 here. And this would be equivalent to saying x squared. Because recall, if you have a square root and you raise it to the power of 2, you're just going to get x. Likewise, if I have a cube root and I raise it to the power of 3, I'm going to get x. So rewriting this, we can say 11 multiplied by the integral of 1 over the square root of 1 minus root 11x all squared dx. And then recall, this just follows the general form that the antiderivative is just arc sine x plus c. And so I'm going to replace it with that right now. So 11 arc sine of whatever is inside of here, which is root 11x plus c. However, we're not done yet. We just have to divide by the derivative of the inside. So and the derivative of the inside is just going to be root 11. And why do we do that? It's because if you take the derivative of this right now as it is, you're going to get an extra root 11, which is not present here. And in order to compensate for that, we need to divide by root 11, or in other words, multiply by 1 over the square root of 11 to get rid of that extra square root of 11. And so we can further simplify this because we can just say, 11 divided by square root of 11, which is just actually the square root of 11 multiplied by arc sine of root 11x plus c. And this is your most general solution. Now on to the last example. This is kind of different from the others. Here we have a definite integral where you're told the value is equal to 2 for this. And you're told to evaluate the definite integral of this with 2 separate pieces. So it's not as bad as it looks. All we have to do is just split this up into 2 portions and just use the information that you're given. So we can say that the definite integral from 7 to 8 of 5 f of x plus 3 is the same thing as saying the definite integral from 7 to 8 of 5 f of x plus the definite integral from 7 to 8 of 3. And don't forget the dx at the end. I always forget. And the reason we were able to do this is because we have a sum here, because we are adding 2 things together, and so we can break this up into 2 integrals like this, and it's going to be the exact same thing as this. And so using the constant multiple rule, we can pull this 5 out in front, plus the definite integral from 7 to 8 of 3 dx. And so you're given in the question that this integral is equal to 2, which is the same thing as you have here. So all you have to do is multiply 5 by 2, and then you just evaluate this integral. And remember, whenever you have an integral of a constant, you just add the variable at the end. And if you don't believe me, just take the derivative of this, and you're going to get the exact same thing that is here. And we're going to evaluate this piece only when x is equal to 8 and when x is equal to 7. So 5 times 2 is 10, and we're going to evaluate the 3x. So we're going to evaluate at the higher number first, and then subtract with the lower number. And so this is going to give us 10 plus 3, which is just equal to 13. So this would be your final answer.